Okay, and I think without further ado, we should invite our next guests, right?
Yes, the next ones are Bob Wijsman and Eleni Ciampali. And they both work at Ubiquity. Bob is head of production, and Eleni is a data engineer. And you're both using Azure Database for Postgres Flexible Server, right?
Yes, we do. Yeah.
Okay, so I think you're the only customer talk in today's live stream lineup. So you're special. You were special anyway. But
yeah, we feel really we are really honored to be in that spot. Yeah.
Awesome.
Thank you, Claire.
Yeah, welcome. Well, without further ado, let's get us started. Bob, you're going to take the lead, right?
Yes. Great. So I'm Bob Huisman. I'm the head of production of data and technology within Ubiquity, and I'm going through this talk with Eleni, who's our senior data engineer. And we were facing the problem of slow queries that were fast previously. And we did a lot of things on performance optimization. We had our indexes straight. We allowed for data wrappers, query plans, etc. And then we ran into the topic of bloat and auto vacuuming. And it was very interesting for us because we have around 80 databases and around 7,500 tables, and these are growing. For the record, we are working on a Postgres single or Postgres Flex server 13.3 hosted on Azure. And yeah, we talk about the journey on how we were managed to set the auto vacuums right for all those different tables. All right. So before we dive into a bit of the content, we want to first introduce a bit to Ubiquity, the challenges that we have faced, the impact of massive bloat, and then we go through the design and the implementation of it, and some important steps of database table segmentation. So Ubiquity is the world leader in media investment analysis. We work for the biggest advertisers of the world, including Johnson & Johnson, Mars, Volkswagen, Unilever, etc. We do not analyze advertisements on individual levels, but we analyze them on campaign level. That has some benefits and also for our clients, of course. So over time, we have analyzed by now 5.5 trillion impressions. So that means that we have analyzed 5.5 trillion pairs of eyes watching an advertisement on any given website. Therefore, our client project dynamics made it pretty hard for us to set out the vacuum settings right. Because as we all know, when a project starts, internal or external, it's very likely that the scope will change. And the further you are on the project, the harder it is to adapt and the more it costs. So during the project, we see many delete updates and additional inserts to comply with the scope, adding a lot of bloat to any table. It can also be that when we are crunching the data and our media analysis is already started, we find some QA issues due to delivered data or other issues in the ETL, and that also returns in deletes, updates, and additional inserts, more bloat. And then we get to the presentation stage of a project where we present our data analysis to the client. They want to know more, they got a better understanding of the data, and that can also result in more inserts, updates, and deletes on data in our tables. As you can see, we accumulate quite a lot of bloat in each client lifecycle. This is how it looks. If you visualize it, normally we would like to see a more sequential approach where we have the bullets next to each other. First you initiate your project, then you do the data crunching, and then followed by a media analysis. Unfortunately, they go hand in hand, and it's up to us to make sure that our processes are as fast as possible, and that we are agile enough to adjust to new client wishes. Meaning then an additional factor that makes it more complex for us to manage all those databases and all those tables is that we were not able to predict what the right auto vacuum settings are at the start of a project, or and therefore the auto vacuum settings and the auto vacuum analysis settings that are set by default by Postgres did only fit a small portion of the tables, as we found out. And monitoring and setting the settings right for 7,500 tables, it's not something that we want to do manually. It's basically impossible. So as you can see, we identified that there were 4 types of client project workload types. Some projects saw a big spike in the beginning and everything smoothed out during the rest of the year. Some had a very stable workload, some had a spike in the beginning, in the middle, in the end, and some just were very random. Yeah, so we had to be able to adapt to it and make sure that our query performance was always on par with the needs of a project and our internal stakeholders like the analysts and the client engagement managers. The ineffective auto vacuum settings accumulated massive bloat because the bloat was not vacuumed correctly, or a vacuum was not started at all, as we have found out for certain tables. The bottom line was the settings by default are not aggressively enough for the bigger table, or too aggressive actually for our smaller tables. We made sometimes a bit a controversial move as we ran some vacuum fulls to remove the excessive bloat and return it to the storage of the server to make sure the tables are clean again, and the query performance actually really improved. And we consider this as the new clean state of a table that we want to maintain at all costs. And with the current versions of PostgreSQL, a vacuum full is not as dangerous as it was in the past. So here you see an example of how a massively bloated table looks like. In the dark below, you see which actually data space is used by live tuples. And then after an insert, an update, and a delete, you get and deletes. You see a light blue bar on top. That's auto vacuumed, and it's kept reserved for a table, which is fine because it makes it easier later on to run updates, insert, and deletes on that same table. However, we saw also a big portion of unvacuumed bloat taking a lot of disk space. So we needed to clean that up and make sure our server was clean and our tables were fast and the query performance was optimized. As said, we ran some vacuum fulls to clean and return excessive load. We tested before and after a vacuum full some basic queries that are executed a lot by our analysts, and they do basically a sum and count based upon the 3 most important dimensions that we have in our databases. And with the new table state, we would consider that as a good state, and that we want to make endure forever. So what were actually the structural performance improvements we made? You can see a good bullet chart of how it looks like. So we returned, by cleaning those tables, we returned 1.5 terabyte of disk space to the server, and that's equal to 30 client databases, which is quite a lot. It's worth for 9 months of new clients, so to say. And we saw 70% average query time performance improvement, which made our analysts very happy, of course. And it depends a bit on what kind of table, of course. And now I want to pass over the stage to Eleni to go through the design principles and how the actual implementation really worked. So Eleni, up to you.
Yeah, hello everyone. I'm Eleni, data engineer at Ubiquiti, and yeah, I will show you more about the technical side of our approach and how we manage to automate the whole process. So yeah, let's start. Thanks, Bob, for the introduction and the business impact that you showed. So I will discuss more about our design principles first. So what our design principles were for this approach? So the first part is that the solution should be run fully automated from end to end. That means that if we have any new client database or any table in the future, this should be automatically included in the solution. Another important aspect is that monitoring and alerts should be there in order to have an overview of the health and correctness of our auto-vacuum settings so that we know what the auto-vacuum settings are on each table at any time. And we wanted all the settings to be transparent to us. And the last one is that the categorization of the table should be dynamic, which means that any table should be able to move between segments at any time based on the current workload. And I will discuss about segmentation in a bit. But before that, let's go to a high-level design of the whole process, including some steps and some applications and tools that we used. So as you can see, we made use of different tools, and starting from the left, we collect different kind of metadata from all our client databases, and we store them into a central metadatabase tables. After that, we made a segmentation and in order to determine the scale factors and the auto-vacuum factors that we want. And as last steps, we store them into another table and update all the factors accordingly based on our segmentation. And this is our whole process and then end pipeline, which is managed by Airflow. So we use Airflow as tool, which is an open source tool which is used to orchestrate all our jobs. And the idea behind Airflow is that we have the whole process into a single DAG. And by DAG is the main concept actually of Airflow. And it includes different tasks which you can manage and orchestrate at any time. So in this drawing here, you can see how our DAG looks like, and you can see that we have different tasks of the process. I will go a bit into them. So some tasks run in parallel while others in sequence, but this is how the whole process looks like. The DAG runs every night and the duration is 1 hour, more or less. And currently, based on the total number of tables that we have, it's around 236 tasks in total that run. So let's make it more clear and go more into the pipeline and the tasks. So first of all, every time that we start the process, we generate a unique ID, which enables us every night. It's good to have a unique ID of the process so that you can log and you can see what goes on there. So after we log the process, we loop through all our client database tables and we execute some analyze command there, SQL analyze command. And we do that in order to get the most updated table statistics. So after we execute the command, we extract the data that we want and we push all the data into a central table. At this point, after we have all the information, we create an access token because we want to connect Airflow with Databricks. And the idea behind that is that in Databricks, we have the whole analysis of our tables, of some of the data we want, like the dead tuples or the live tuples of each table. So we do some analysis there and we do table segmentation. So create different segments and different categories for each table. After this step, we update, and having defined the auto-vacuum settings that we want, we update all the factors and the settings accordingly to each table. And again, this is done with Airflow. Once more, I will go quickly through the steps just to make it more clear. Actually, I will discuss about the main steps. So first thing that we do when we are on a database table, we execute analyze command to get the most updated table statistics. We extract the statistics. Some of the important features are the rel tuples, which is actually the number of rows, or the dead tuples. Then we push them in some tables that we have, central tables, aggregate information there is pushed. Next step is to create a connection between Airflow and Databricks, and this is done using service principles. And after we have the connection, we initiate a Databricks job from Airflow. And actually in this job there, the whole analysis is performed from end to end. And table segmentation is done and optimization of the factors is done. And then as last step, we extract the segments that we have been created based on the analysis, and we update all the out-of-vacuum factors accordingly on each table based on the segment that the table belongs to. So that's it for the pipeline. Next, I will tell you a bit more about the analysis and the formulas that we used. So this is a snapshot, a bar chart actually, of at a specific workload and how our data segments distribution look like. And you can see that we have defined 7 segments in total, and you can see different number of tables fall under each segment. And I will discuss first segment 1 to 6 and how the out-of-vacuum factors were defined there. So the segment categorization, it was done using a density ranking function, which is a Python function, and with some adjustable weights. So using this density function and the deviation of the rel tuples and the dead tuples, each table was assigned a score. And this score is defined in the formula below, and it's a custom formula that we defined, and we made use of the rel tuples and the dead tuples. And you can see here that we have 2 factors. So using those 2 factors, A and B, we can adjust them accordingly. And this is based on this score, we create the scale factor of our out-of-vacuum for each table. That's all for the more optimized way or the more optimized segments. But for segment 0, the first segment actually, we need to follow a different approach there because this segment includes only outliers, so tables that have very high volumes of data. So we needed to take care of them. So for that, we used a more aggressive formula, and we had to define the factors manually. But of course, this was again done after some investigation and analysis. So for this segment and the tables that fall under this segment, we set the scale factor to 0 and the out-of-vacuum threshold to 200,000. And you can see in the formula below how the threshold is defined using the total rows and making use of the factors and the threshold of out-of-vacuum. Yeah, that's it from my side. Bob, are you ready to wrap up?
I'm ready. Thanks, Eleni. A great explanation, I think, of the technical setup. It's quite a journey to get there. So to wrap it up, with this approach to have a dynamic table segmentation and adjust different out-of-vacuum settings to those tables, we made significant gains that are sustainable over time. We were able to save a good 1.5 terabyte of data, and which is equal to 30 client databases, which is quite a lot for us. The end-to-end automated pipeline makes make sure that the settings are always optimized, and we don't need to make any manual adjustments now on it because it's runs every night, and when a new database is created, it's included there as well. When you copy this, when you also would like to work on this project, make sure that you are monitoring it closely as well, because different segments might require different formulas, as we have found out. And with the right alerts on the pipeline and wise monitoring tools on Airflow, we are able to spot any issue with the pipeline or any abbreviation of our normal durations. And of course, there are many other factors that can be taken in consideration for auto-vacuuming. I think a lot of has been covered by previous speakers, like cost limits and workers. We haven't touched that in this project yet, because we first wanted to review the solutions when this project was running for some time, and but it's definitely in the scope for the future. At some point, we were in a dead spot with a project, so we want to acknowledge some people, or one of the people of Microsoft Azure Database for PostgreSQL Server community. We want to thank Gayatri Paderla for her help and time to help us over that moment, and also Alicia Kucharchak, who helped us with some examples and good materials to go through, and Sunil Argawal, who pointed us to the right people and right resources for this project and also other projects. So thanks a lot for helping us. I hope you learned, everybody who was watching learned something from this talk as well, and how it can speed up your business. If you find yourself vacuuming your house afterwards, sorry for that, there's a lot of vacuum talk going on today. And if you have any questions, please let us know on the CytusCon channel, and we're happy to respond.
Awesome. Thank you so much for joining us, taking time out of your regular workday to tell your story.
Our pleasure.
Our pleasure.
Yeah, it was a very interesting story. Well, one thing that I was wondering though, why are you running so many databases on one single server?
It's kind of a legacy reason, as we started as a couple of years ago as a small startup, and only needed one database server basically, but we grew exponentially fast. We're acquired by Ubiquity 2 years ago, and we are about to migrate in our current tenant to the Ubiquity tenant, and we thought it was easier to only switch one database server and then split the server up into smaller servers, and then do it before the migration. So maybe next year there's a talk about how you migrate your server.
Well, I just wanted to remind everybody who watched your wonderful talk that I'm popping up a banner on the screen, that there is an attendee survey, and it's not just about the event, but it's about any of the talks that you might have watched. And I'm sure both of you would love feedback. So if people have a chance to go do that, I would really appreciate everyone in the audience doing that for the talks you've watched today. And Eleni, ευχαριστώ πάρα πολύ. Bob, thank you for joining us. And yeah, we'll see you on Discord.
Thank you. See you there.